This is very nice, isn't it? Fancy new screen. Yes, all right. Good evening, hello, welcome. I'm back. I was, as most of you probably know, I was at the ISO C++ meeting in Belfast last week, so I'm a little bit behind the curve this week, a little bit rushed, so apologies for being late, and apologies if tonight is not quite as polished as it would normally be. Normal service will be resumed next week, I promise. So, as Tom mentioned, this is session 6 of our initial C++ module, our introductory module. This is the last session of this module, so by the time we get to the end, you will have completed module number 1. So next week we'll be going on to our second module, which is all about custom types. It's about writing your own types, writing your own data structures, so you can write sort of useful, realistic programs. It's really exciting, obviously. It's going to be great, and I look forward to seeing you all there. Obligatory feedback slide, because I have to do it every single week. And in fact, we do have one new person this week, so welcome to you. And also for the benefit of anybody watching online who is watching for the first time, hello. We have our own room on the CPP Lang Slack. So we encourage everybody to join. Go to that URL that's on the screen, slack.cpp.al. You can pop your email address in there. It'll send you an invitation, and then you can join the CPP Lang Slack. This is a Slack group that's got a few thousand members for discussing the C++ language, and in particular, we have our own chat room in there. It's #C++, #CPP London Uni. So please do join us in there. And there's also another thing worth mentioning, if you haven't discovered it already, there's also a #learn room in there, which is, again, it's not run by us, but it's got lots of C++ learners from around the world, and also a lot of C++ experts who like to hang out in there and answer questions. And so that's a great resource if you have any questions and we're not around to answer, or you want better answers, but anyway. So, as I said, I wasn't here last week, unfortunately, but I have caught up. So, correct me if I'm wrong, last week you talked about the auto keyword.
Yes.
Okay, agree with me if I'm right. You talked about the auto keyword.
Yes.
Yes, you talked about pass by reference.
Yes.
And you talked about the const keyword. Are these things all true? Yes. So one person did concentrate on const. Everyone else had sort of fallen asleep by then. Okay, that's good. That means you've covered the things I thought you were going to cover. So this week we are going to, we're going to just have a little bit of revision about const and references, and we're going to go on to talk about something that has a very long name. It's pass by reference to const. All will become clear in about half an hour or so. We're going to talk about how the auto keyword interacts with const and with reference semantics, which actually makes sense. It's just perhaps not immediately obvious how it all works. And then finally, the last thing we're going to do in this module is we're going to talk about namespaces, why they exist, what they are, why they exist, how to use them yourself. Okay, so that's the plan of action for today. We are a little bit curtailed. Apologies for that, but we'll do our best to get through it.
Did you plan a test?
I'm sorry?
Have you planned a test?
Next week.
Oh, yes.
I'll talk about that. Don't worry. Okay. References. So I've said this many times now, I'm sure Ollie said it last week, is that C++ uses value semantics by default. And what we mean by that basically is that copies are independent. If you copy a variable and you modify the original, you modify the copy, the original is not changed. Right, the two are completely independent. So a good way to think about this is, like documents on your computer, right? If you have a Word document and you create a copy of it, and then you change one of them, the other one doesn't change, right? They're independent copies. They start off with the same value because they're copies of one another, but you can change them independently and they don't affect each other. But C++ also supports something called references. And we create a reference by using this ampersand symbol, the and symbol, after the type name. So given an int I equals 0, we can create a reference to that int, which here I've named ref. We've initialized this reference to point at the same bit of memory as I. And the difference in this case is that modifying a reference also affects the original variable. Okay, so this is the exact opposite of value semantics. This is reference semantics. One way to think about references, you might find handy, some people do, is as if you're giving a new name to an existing variable. Right? A new name. So I is like a name we give to a few bytes in memory. And by creating a reference, we're giving a second name to that same few bytes of memory, if you want to think of it like that. Another way of thinking about it, if we go back to our Word documents, is rather than creating a new copy of our document, we open a second window that is looking at the same document. And when you type words in the one window, those words appear in the other window. And when you type the words over here, they appear in the first window, right? They're two windows for looking at the same value. Okay, is that clear? Understandable? Good. Yeah.
Is that a semicolon on the I?
It is, it's just the display's gone a bit funny, yes. So let's have a look at a little example. Just as we had on the previous page. We've got an int I, initialized to 0. And then we've got a variable named ref of type reference to I. Right, so we read types in C++ from right to left because it's weird. So this is a reference to an int. And we say we set ref equal to 42. Say ref equals 42, and then we print I. So what is this going to print out? You all nodded when I said the thing about the window. Sorry? 42? I think you've basically got two choices. You've either got 42 or 0, right?
If it affects previous the I, it should be 42.
Yeah. Yeah. So this is going to print 42. Because ref is like a new name for our variable I.
Small technical issue. On YouTube, we have a quite big screen cut out. I'm not sure if you set up the screen.
Restart the canvas.
Okay, can I do it when we have a bit of a break? Right?
Okay, thanks.
It's visible, right? It's just small.
How bad is it?
Part of the screen is cut.
It's cut off.
So
basically.
if we
Cut
go
below the screen.
two lines down, you probably will cut off.
Okay, technical pitch.
Sorry.
Ladies and gents, sorry about this. Back in a moment.
Got it?
Just go back to. Oh, you stopped it.
It won't let you change the canvas size. It won't let you. Anyway.
Okay. Well, we.
Right. Apologies for that. Where were we? Okay. So we create an int I, then we create a reference to I. We change I via the reference, and when we print out the value of I, we see it has been changed because ref and I represent the same variable, the same bit of memory. So everything we do to the reference affects the original variable. Okay? So this is kind of very important. Right? So I want to make sure everyone's kind of clear on why this is happening. Right? The difference between reference semantics that we're using here and the value semantics that we normally use where we have independent copies. The difference that this little ampersand here makes. Yeah.
If you put the ampersand beside the ref, would that be a reference to a pointer?
So if you put the ampersand where?
Ref beside ref. Because I did it like for a couple of weeks and I remember the ampersand in front of like a
He's
variable.
asking.
If I put the ampersand there,
That's a reference.
that takes the address of a variable. It has a different meaning. Yeah, well, that's pointers that's away down the track. We won't worry too much about that
The
yet.
video there means on high.
Oh, sorry, yes. If you put the ampersand, if you said ref equals ampersand I, that would be the address of operator, which is a sort of related but different meaning of the ampersand. So is everyone's clear on why this happens? What's going on here, right?
So
Yeah,
accessing with a different name.
You're accessing the same bit of memory via a different name, absolutely. Okay, so now I'm going to create a vector of ints, vec, and initialize it with 1, 2, 3. And now I'm going to do something fun. You might not have seen this last week. I'm going to use a range-based for loop. Remember last time I was here, we were talking about the different kinds of loops. Mentioned that range-based for loops are really cool. And what we can do is we initialize our loop variable as a reference this time. So there are two common uses of references. One of them is its function parameters. The other one is this, range-based for loops. So what this is saying is, as we iterate over our vector, for each element in our vector, we're going to create a reference to that element. And within our loop, that reference has the name I. And we're going to set I equal to the value it had before, times 2. And after we've done that, our vector now contains the values 2, 4, and 6. So for every element in our vector, take a reference to it, set the value of that reference to twice what it was before, and then move on to the next element. So this is a way that you can modify container elements in place. Right, very, very useful. So what would happen if I got rid of that little ampersand, if it just said for brackets int I colon vec?
0.
Sorry?
So 0.
It would be 0.
Some kind of error message.
Some kind of error message. What would be 0? Vector. Not quite. Yeah. It would create a copy of every element and yeah, so what would happen is if I did not have this ampersand in the for declaration, then we'd create a copy of each element as we were iterating through our container.
Ask the key question.
Sorry?
What would happen to vec?
Well, I thought I did. Well, yes, what would happen to vec after the loop had completed?
What would be in vec if it wasn't int ampersand? It was just int.
1, 2, 3.
Yeah.
It wouldn't change, right?
1, 2, 3, because we'd be creating a temporary copy of each element. We'd modify the copy and then throw it away, right? So we wouldn't affect the original container in any way. But doing it this way, by taking a reference to each element as we iterate through it, we can modify the container in place. Okay, so just another use of references you might not have seen last week. By far the most common use of references is not for local variables like we were doing there. I mean, yes, they get used in for loops, but by and large, most of the time that you will see references in C++ is as function parameters when we want to use pass by reference. So I've said this many times already, but usually when we call a function, that function is passed a copy of each value that we give it. And this is called pass by value. By and large, you can divide programming languages into two kinds. Either they're passed by value or passed by reference. C++ is kind of unusual in that you can do both. You can choose which one you have. By default, it's passed by value. But if we make our function parameter a reference type, that is with the ampersand on it, we get pass by reference instead. And what this means is that the function operates directly on the passed in variable. Right? Not a copy. It operates directly on the passed in variable. There are no copies taking place whatsoever. And this can be a very good thing. For example, if we have an enormous vector of millions and millions of elements, millions of strings, let's say, that can be a lot of memory. If we have passed by value semantics, when we call a function that operates on that vector, it means we have to create a copy of the vector, a deep copy. We have to copy the vector. We have to copy all of its contents, which means copying each individual string. This is going to be really slow. It's going to use a lot of memory. It's not what we want to do. But if we use pass by reference, then no copy takes place whatsoever. Right? It's much faster. So let's have a little look at what that looks like. So here I've got an inspired name. I've got a function called myFunction. Returns nothing. It takes two parameters. One of type int and one of type reference to float. Oh, let me just, I've changed the names in one place and then I didn't change them in the other. 2 seconds, sorry. So what this function does is it sets val equal to 100 and ref equal to 3.142 floating point. So now in main, we're going to create two variables, an int and a float, I and f. Because again, I'm really inspired when it comes to naming. And then I'm going to call my function, and I'm going to pass these two variables that I've just created, I and f. So, here's a question. What happens, what are the values of I and f after the call to my function? Once my function is run and we're back down here, what values do I and f have? You've been doing this too long, Sarah. Someone else. Someone could yeah, go on.
0 and 3 and a bit.
0 and 3 and a bit is the right answer. Yeah, 0 and 3.142. So why did you give that answer?
Because the reference is updated and the copy is updated in the function, but is not updated by reference. So the origin is the same.
Absolutely perfect answer. So my function takes the val parameter by value and the ref parameter by reference. So inside the body of my function, we set val equal to 100 and ref equal to 3 point whatever. But val is a copy of the thing that we pass to it. So sure, we can change its value, but at the end of a function, it's just going to be thrown away. Val is just a copy of I. It doesn't affect I. On the other hand, ref is a reference to the variable that we pass in. So ref is a reference to this guy here, this float f. So when we change the reference, or when we assign through the reference, it is updating the value of f via that reference. It's as if we came up with a new name for f inside this function. So if we print the value of I, this is going to print 0 because I has not been changed. And when we print f, it's going to print 3.142, possibly with some trailing zeros, I can't remember. Because we passed by reference. So this is, in essence, this is the difference on one slide between pass by value and pass by reference. Okay, so this is, again, pretty sort of important fundamental stuff to kind of make sure you understand. So that's why I want to spend just a little bit of time revising the material from last week to make sure it's crystal clear in everyone's mind what's going on.
If you didn't use the pass by reference there,
Yeah.
would it just print whatever the variable float that's in there?
Yeah, so if my function didn't have this ampersand in the after float, then again the float would be copied into the function. The copy would be updated. We don't care about that. But it wouldn't update this original variable f. Come in. Okay, so we can pass by value. It means we copy in, and then that doesn't affect the original variable. Or we can pass by reference by declaring our function parameter to be a reference type, that is the type name with an ampersand on the end. And when we do that, any modifications we make through the reference are reflected in the original variable.
So could you use this function to, like, assuming you had like a separate file, and just pick up the values from there and pass that, and do references? The reason I'm asking is there's a lot of testing we do at work, and I've been trying to figure out how I can maybe use something we've learnt here.
Yeah.
To kind of we tend to have a lot of parameter files, which we have to update daily to do deployments, and it's really tedious.
Yeah.
So when I look at what you're doing, I'm thinking, would I be able to pick up the values from another file and pass them temporarily and have like an output with the new?
You absolutely can do that sort of thing in C++, yes. Yeah. So
Is it really advanced than what we're doing here?
so the question was about can you sort of load values from a file, say update those, use functions to update those, and then write them back out to a file. And yes, you absolutely can do that in C++. There is a class that's called standard fstream, it's a file stream, and you can use that to read from a file and write to a file, write to another file, or the same file again.
We're not going to do that here.
We're not going to do it today. We may get onto it at some lesson in the future, but certainly if you come along on Thursdays, then Ollie will be able to tell you a bit more about that and possibly show you some examples.
Can I have a question?
Yeah.
If we want to modify a value, unfortunately, so we need to use the ampersand, right?
Yes.
Without ampersand, we want to change.
Well, I mean, you can use the original name that's I. So
Yes.
in down here, you could say like I equals 4. That would be fine. But if you want to modify it inside a function, then you have to pass by reference. Otherwise, the function receives a copy. And
Or let's say if I use a global variable, same way I can use in the function.
well, a global variable is different because that name is accessible from everywhere else in your program. but don't use global variables.
Yeah, avoid global variables.
Yeah, they're bad.
Side effects that you can't predict are bad.
All right. So that was references. Let's talk about const. We're going to talk, well, let's talk about immutable values. Does everyone know what immutable means? Cannot be mutated, cannot be changed. Immutable, it's fixed. It's constant. So very, very often, when we're writing programs, we have some variable, we need some value, we calculate that value, we save it, and after we've done that, we never need to change it again. Right? This is extremely common. And C++ has a keyword that helps us out. That we can tell the program, okay, this variable is never ever going to change again. Right? We can mark a variable as const, and that means that that variable is immutable. Once we have initialized it, once we have given it a value, its value can never ever change again. And if we make any attempt to modify a const variable, we're going to get a compile error. And the purpose of this really is to help us out, to stop us from, or to help us not make mistakes. It helps ensure the correctness of our programs. That's the point of the const keyword, essentially. Some people claim it helps with optimization, and you hear arguments for and against. I'm not enough of an expert in how compilers work internally to know whether that's true. But what it really does help with is correctness. Because in C++, we strongly prefer compile errors to runtime errors. Because a typical program, let's say you're deploying to a large company, your program, you might compile it once and it might be run millions of times. So it's much better to catch to find as many errors in your program as possible once when you build it, rather than a million times later when everybody is running your program and they get that little error dialog pop up and it's really annoying. So C++, we strongly favor compile errors, and const helps us ensure the correctness of our code by preventing us from modifying things that should not be modified. And it's actually really handy to get into the mindset of const by default.
Const correctness.
Yeah, so the not modifying things we shouldn't go, there's a term for that, which is const correctness. This is, ensuring that this immutability is handled correctly by all aspects of your program. So a really good mindset to get into is const by default. So when you write a variable, the first time you write it, make it const. And then only later, if you find that you do need to actually modify this, you can delete the const keyword again, right? What's the benefit of such an approach? Again, it's about the correctness of your code. It helps prevent errors, because as we'll see shortly, if you try and pass a const variable to a mutating function, the compiler will stop you from doing that, right? So it prevents things from being modified when they shouldn't be modified. This is actually something that modern languages, in Swift and Rust, have really, really doubled down on. So in C++, things are mutable by default, and you opt into being const, whereas Rust actually takes the opposite approach, that everything is const by default, and you have to add a keyword if you want it to be mutable. And Swift as well, you have I think the keywords are let and var, and they encourage you to use let by default, and then only var if you actually need to change something.
the bottom line on it is that just because in your head you think you're modifying the correct variable doesn't necessarily mean you are. And if you happen to use the wrong name and try to modify something you're not supposed to, because you're being const correct, you'll realise your mistake when you try to compile it because it was a const variable. So start with const, delete it when you genuinely need it, and you will detect more errors. But it's questionable.
Oh, hi.
Are there any speed benefits or penalties?
There are certainly no penalties. There are some experts who will swear blind that const makes absolutely no difference, doesn't speed up your programs. There are other people who say, well, in some limited circumstances, you're giving the compiler a bit more information and it can perhaps optimize things a bit more. But certainly don't think of const as a performance optimization. It's possible it might be in some circumstances, but that's not really the point of const. The point of const is for correctness.
I think it's more like you look at the implementation of a function and you see that it's const and you know that's not being changed in the body of the function.
Yes, well, we'll talk about passing by const reference in a minute, yeah.
Well, const reference, okay.
Yeah, which is really how it's useful because you can look at the signature.
Yeah, const
and,
reference,
yeah.
you know, there's not like that is not being mutated, so you think less when you see the code.
You know the function is safe.
Yeah.
You know that there are specific arguments, it's not changing data from outside, because like there are cases like there's difference between a const reference and just a const by value argument that can be misleading though.
Yeah. The other thing to mention, it's a bit sort of beyond the scope of our classes for the moment, but when you get into multi-threaded code, it can be it's a real problem if you have lots of threads trying to write to the same bit of memory. Whereas if your variables are const, well, it's fine to have lots of threads reading from the same bit of memory at the same time, as long as no one else is changing it. So const can be a real help, especially when it comes to writing multi-threaded code that works correctly. Thank you, Tom. Yeah.
What's multi-thread like? Running different bits of the whole program in parallel.
Exactly that, yes. So again, we'll run through a little example of the const keyword. So here I've got a function print float. Just takes a float f and prints it out, followed by a new line. Same as we have seen dozens of times already. Does this function take its argument by value or by reference?
Value.
By value, yes. There is no ampersand there. This function takes a copy of each float you pass to it. Okay, so I have created a variable pi, type const float. I've set it to an approximation of pi. So now I'm in Alabama and I want to set the value of pi to be 3, which they actually tried to pass a law in about 1880 to do this. But anyway, is this okay? Is this okay? By what I mean is, if I try and compile this program just as it's written there, assuming I had a closing curly bracket for main, is that going to work or is it not going to work? Hands up for it's going to work fine. Hands up for it's not going to work. Hands up for I have no idea what you're talking about. Hello. Don't worry, you have come in, as I said, at the end, right at the end of our initial module. So actually I should have mentioned at the beginning, and for the benefit of anybody who's watching online, all of our course materials are available on GitHub. I'll put the URL up at the end. Well, I can tell you now, it's github.com/CPP London Uni. Sorry.
Videos on YouTube.
Yep, and we have a YouTube channel as well, youtube.com/CPP London Uni, and the videos of our previous sessions are on there. Unfortunately, we had a technical hitch with a couple of the videos for this module, but you can actually find previous installments when we've done this module before. So there's the material is available. Just unfortunately, we had a problem a couple of weeks ago.
And you can always come to the Thursday workshop, and we can get you up to speed as well.
If that didn't come out, Ollie says you can also come to the Thursday workshop, and we can get you up to speed as well. Okay, back to the question. We have a variable named pi. It's a const. And now we're trying to modify the value of pi. We're trying to set pi equal to 3.0f. Is this okay? Well, everybody gave the correct answer. No. This is a compile error. Okay? Const variables cannot be changed after they have been initialized. So the compiler will give you an error and it will tell you pretty much exactly what I just said, word for word. Attempt to modify a const variable.
And compile errors are the best kind of error because they don't upset your customers. Unless your customers are also developers and you're shipping a library, and then they'll be very angry.
Okay. Example 2. Const float e. So I declare a float, and then I set it, I initialize it to 2.718 Euler constant. Hands up who thinks this is okay. Hands up who thinks this is not okay. 2 people. Who's not sure? Yeah, this case is a bit more subtle, right? Because I've said several times you can't change it after you've initialized it. And this guy E is not initialized up here. But actually, this is a compile error. In fact, it's a compile error twice over. Because when we declare a const variable, we have to initialize it there and then. We cannot have an uninitialized const variable. And this is a bit weird because this is actually all right in C, or at least some dialects of C. You're allowed to do this, but in C++ you're not. Right? This is a variable. This is an error twice over. First of all, because we have an uninitialized const, and then we're trying to modify. Well, even if this worked, this second line would be an error because we'd be attempting to modify a const variable. What on earth is going on over there?
They're having fun.
Yeah. Pub time started early. So this is in fact 2 compile errors. So we must give our const variables their one and only value at the time that we declare them. Okay. More tricky questions. I'm creating a variable pi2 equals pi. Who thinks this is okay? Majority of hands. Who thinks this is not okay? Who's not sure?
Doesn't compile.
Well, there are a lot of hands that didn't go up for any of those 3, but.
Who thinks both of the answers are correct?
Technically, as a pedant, none of it's okay because it already doesn't compile.
Oh, I mean, if you were to consider these bits in isolation, right? This is fine. This is perfectly acceptable. Because remember, value semantics by default, we're creating a new independent variable. We're initializing it to have the same value as pi, but that only requires reading the current value of pi. We're not modifying the existing pi variable by doing this. Okay? Pi and pi2, by this definition, are completely independent variables. And finally, I'm going to call my print float function, and I'm going to pass pi. So pi is a const float. Our print float function takes plain float f.
You're passing pi into the function.
I'm passing pi into the function print float. So who thinks this is okay? 3, 4, 5. Who thinks it is not okay? 2, 3. Ah.
If you would try to modify it inside the function, there would be an error. But otherwise, I think
If you were to try to modify.
inside the function.
Hang on.
So
Yeah.
if the f is passed.
Okay, so what if I, instead of the print
Actually, no,
float,
sorry,
I
it's
said
passed-
like
no,
f equals
sorry.
99?
No, it's sorry, it's okay because it's passing it by value, so it's okay.
It's the copy, right? It's a copy. So
Exactly.
that is discarded by them, but
Yes.
not changing value.
Fantastic, well done, yes. So print float, the way I've written it there, it takes its parameter by value. That means it receives a copy of the thing we give it. So we can perfectly well modify f inside our function here because we're only operating on a copy. So in order to create that copy, we only need to read the value of pi. We don't need to modify pi in order to create a copy of it, as we've just seen on the previous line. So this call is perfectly okay. What I could not do, yeah.
But from last, like from what I understand from last classes, the keyword should be a part of the type, so float and const float should be other types.
That is entirely correct. Float and const float are different types. However, we can initialize a float using the value from a const float.
So there's like typecasting involved.
It's not typecasting exactly. It's that float and const float are different types, but they are closely related types. So const float is what we call a qualified type. Right. Let me just answer this question then. So we can initialize a float from other related types. So we can initialize a float from an int, for example.
And that's not casting?
That's
resulting in casting?
it's better to call it a conversion.
Implicit conversion.
And in this case, an implicit conversion. There is an implicit conversion from a, well, we can initialize a float from a const float. That's fine because all we're doing is reading the value that the initializer has and then creating a new variable that has the same value. Right?
Would be much.
It's not, casting has a, sort of strictly speaking, a different meaning, which is sort of forcing the compiler to regard something as having a different type. Right. So again, I get what you're saying, just slightly different terminology, I guess. Yeah. Sorry, you had a question.
I cannot use const to initialize a variable or
You
is it possible?
You can use a const value to initialize a variable, yes.
It's possible.
It is possible, yeah. Yeah. Because creating a new variable just creates a copy. In
Yeah.
order to create a copy, we only have to read the
Yes.
source value. Was there a question? Did I see a hand up somewhere? No?
Can I question? If I want to modify that f in a function,
In here?
yes, so it has to be ampersand or without ampersand will work too.
Okay, so within the print float function, I'm just going to spend all day all evening asking you lot questions because it's far easier than thinking myself. If inside my print float function I were to modify f, or attempt to modify f, if I say I had a line in there that said f equals 99, semicolon, is that going to work?
Yes.
Yes. Yes, because this takes its argument by value. So this f in here is a completely independent copy that we can modify, mutate in any way we like. And because it's by value, it doesn't affect the original variable. Now, if my print float function operated by reference, if there was an ampersand after the float, between the float and the f,
Can it be beside the f as well? That's what
it can be beside the f, yes, that's where it's a bit confusing. And that's why I like putting it against the type, because it otherwise it can be very confusing with the address of operator. So I prefer to sort of make it hug the type, but like in terms of how you write it, C++ doesn't care about the white space. If print float operated on a reference, then we'd have a problem. Then this line would be an error. But we'll talk about that a bit more in a second. But to conclude, yes, as written, this call is absolutely fine. We're just going to pass a copy. We can take a copy of a const. That's no problem. So we have references, we have const. What happens when we put the two of them together?
Question. What
Yeah.
would happen if pi was const, float, and then ref?
If pi was, so in this example, so just in main, if I just declared const float ref pi equals whatever, that would actually work, but it's actually what I'm going to talk about now is exactly what would happen there. Okay, so we talked about references, these little ampersand things. We talked about the const keyword and how it stops us from changing things when we don't want to change things. We can put the two of them together. We can do the two things at the same time. And it looks like this. So here we've declared a variable named I. It's a const int. So we've given I the value 0, and that's the only value it is ever going to have. But now we declared this thing RCI, which, remember, we read type names in C++ from right to left. So this is a reference to a const int, which is why I named it RCI. So this is where the type thing you were mentioning. If we didn't have the const on this second line, it wouldn't compile, right? Because we'd be attempting to initialize a mutable reference from a const value, and that's not allowed. So this second line here, const int and ampersand RCI equals I. This is initializing a reference to a const int. At least that's the proper name for it, but most people don't refer to them like that. We usually just call it a const reference. Personally, I refer to these things, at least for the purposes of this class, as a read-only reference, because I think it makes it a bit more clear what's going on. So I'm going to try and use the term read-only reference. The majority of C++ users will use the term const reference. The proper sort of language lawyer term would be reference to const, but they all mean the same thing. They all mean a reference to a const type. In this case, for example, a reference to a constant. And read-only references, const references, are pretty special, and they're pretty useful, and they're extraordinarily useful as function parameters, as we will see very shortly. So if we have an immutable variable, a const variable, and we try and initialize a mutable reference from it, that's going to give us a compile error. So you notice on this second line, I'm just saying int ref. That's how we say it, reference to int. This is saying this is a mutable reference, a reference that I can read through and write through. But CI, the thing that we're referand, the thing that we are initializing this reference to, cannot ever have its value changed, right? Referand, yeah, I don't know.
Referee.
If this was allowed, this would give us a way of modifying CI by giving it a new name. Remember, you can think of references as like a new name for one bit for an existing variable. So this guy here is int and ref. This is a mutable reference. It's a reference that we can read through and write through. And we're attempting, with the code that's on the screen, to create a new name for our variable ci that we can use to read and write? Well, no. That's not allowed. So if we tried to do this, the compiler, again, would give us an error because this would be violating the const correctness of our code. The other way around, however, that's allowed. So here I've got a mutable int I. We're free to change the value of I, set it to 900 or 10 million or whatever we wanted to do. And now I am initializing a read-only reference to I. So cref is a reference to a constant. It's a read-only reference. This is saying, okay, it's a only reference that I can only read from. But I itself, we can read and write, right? So this is restricting what we can do. And that's okay. This is trying to allow us to do more than we could before. That's bad. This, we're just restricting what we can do. So that's fine. Question, Saad?
Yes. So, but later on, if you did change I, const int ref, cref would equal the updated value.
It would indeed, yes. Yes. So the question was, if I modified I, which I'm allowed to do because I is not const, if I modified I and then read through cref, say printed out cref, I would see the new value of I. Because I and cref still refer to the same bit of memory. It's just that I'm allowed to change it using the name I. I'm not allowed to change it using the name cref. So importantly, why does it do that? That's very annoying. But it doesn't mean that I itself is not changed. I is still mutable. It just means that we cannot use this new name to change it. It means the new window we have on this bit of memory is read-only. So other than the fact that the screen has chopped off the essential lines on this slide, is it clear why the first one is forbidden and the second one is permitted?
Yes, no?
There were nods. There were nods. So the fact that we can initialize a const reference, a read-only reference, either from a mutable variable or from a const variable, means that we can use this pattern of pass by const reference, pass by reference to const, kind of properly. And this is by far the most common use for these read-only references. In fact, it's by far the most common kind of function parameter in C++, I would say. This is the best of both worlds, because this avoids the copying that we were talking about before, that happens when you pass by value. But it means that we know that within the body of the function, that function cannot mutate any variable that we pass to it. Right, this is great. This is, in fact, how you will, once you kind of get the hang of how it works, this is how you'll find that you pass variables to functions most of the time, is by const reference. And in fact, a really good rule of thumb, this is what, our second so far tonight? Yeah. If you have a built-in type, say an int, a float, a bool, char, whatever, for built-in types, you can pass them by value. But everything else, any like user-defined types or these things like vectors and strings, pass those by const reference, by reference to const, by read-only reference. Make your function parameter a read-only reference to these types. And this is the fastest, that is most performant way to code functions in general. There are, of course, exceptions, as with everything in C++, but a really good rule of thumb is to remember this. If it's a built-in type, pass it by value. Everything else, pass it by const reference. And use a mutable reference, that is just like type and. Use them rarely and only when you actually need what we would call an out parameter or an in-out parameter. Yeah.
Why is it good for built-in types?
That's a good question, because the built-in type. So why have this exception for built-in types? And it's because they're generally very small. There are a few bytes in size. So a bool is 1 byte, an int is typically 4 bytes, float typically 4 bytes, and it means that these things can be passed very cheaply. In fact, they can usually be passed in registers, which makes them very, very fast to pass to your functions. Right? References. Those who don't know what I'm talking about can switch off for a second. Behind the scenes, references are usually passed by pointer, so it's an indirection. So that can typically have a tiny, tiny bit of overhead that's much, much less than actually copying the variable value if it's a big type, but it's slightly more expensive than passing something very cheap like an int.
Which would matter if you're doing a large for loop or something other.
No, it would matter if you are like, I don't know, doing like high frequency trading where you need something to work in microseconds or you lose millions, or you're writing a game where you have to update 10 billion polygons on the screen every 60th of a second, right? That's the circumstances in which this matters. But C++ is all about performance, so it's kind of good to get into the habit of doing it the fastest way, just automatically. Yeah.
So the question is, why would you leave like performance on the table if you know that it works?
Why would you leave performance on the table? Exactly. This never hurts, and it might win. So yeah, it's a good habit to get into. Do you have a hand up? No. Oh. So let's show you what I mean. I like print functions because they're just really easy demonstrations. So I've got a function that takes. It's called print vector. It returns nothing, and its argument type. Remember, right to left. So it's a reference to a const vector of strings. So a vector of strings is potentially many, many megabytes in size, right? If you have a vector that holds like, and each string holds the complete works of Shakespeare, that's going to be multi-megabytes in size. We don't want to copy that unnecessarily. As Michael just said, why pessimize yourself? Why leave performance on the table? But we're just printing something. We're just reading it. So we don't need to take this by mutable reference. We can just pass a const reference, a read-only reference to this vector. And then again, I'm showing off just because I can, just to show you another use of this const reference thing. Is that again we can use it as the initializer in a ranged for loop. So now we're iterating over the vector we were given, and we're gonna, for each pass, for each element in our vector, we're going to initialize a variable str, and that variable is a reference to a const string. So we're not copying, imagine that each string inside our vector holds the complete works of Shakespeare, right? These are big strings, we don't want to copy them unnecessarily. So we form a reference to the string, but we're not modifying it. So we form a const reference. Const by default, again, really good mindset to get into. Also, the non-const reference wouldn't work in this case, but don't worry about that. And then we're just going to print out each string, followed by a new line. Just going to print out lots and lots of copies of Hamlet or whatever. Then in main, we create a vector with two strings in it. And then for no particularly good reason, we add a third just by via a pushback call. And then we call print vector, passing in this guy here. So in main, our variable vec is mutable. We can change it. That's why the pushback call works. If we had declared this const, then pushback would give us an error. However, we can still initialize a reference to a read-only reference from our mutable variable. That works fine because we are restricting what we want to do. We're not trying to do more than we could to start with.
What's pushback? Is that like pushing it onto the object?
So vector is like a what they call like an array or an array list in other languages. So pushback adds a new value to the end of the array, expands the array, adding a new value on the end.
There's another command, in place back.
Yes.
What's the difference?
So in place back can sometimes be an optimization because it can sometimes avoid doing an unnecessary copy or move. But it doesn't work with all types. For the purposes here, I only use pushback. Later when we learn about constructors, you'll find out what in place back does. It calls the constructor in place using the arguments that you provide. It's a variadic function. It's a bit more complicated than we want to go into today. So, pass by const reference is awesome. You will use it most of the time. It avoids potentially expensive copies. And the other thing to say is that usually you don't want to have to trawl through the actual source of a function to find out if your variable is going to be mutated. Let's say this wasn't called print vector, which makes it nice and clear what happens. Let's say this function was called frobnicate. Right? All you have to do, if you are writing this bit down here, you just have to look at what we call the signature of the function, that is its name and the argument types it takes. You only have to look at the signature and know that frobnicate cannot possibly mutate your vector. You know that when you're down here, after this call to frobnicate, that vec is going to have exactly the value it did before, right? That's extremely useful information to have. All make sense? Awesome. Right, so last week was auto, references, and const. We've just talked about the interaction between references and const. Well, let's add one more keyword to the mix. Let's talk about how const and references and also how these three things interact with each other. This actually is, once you sort of work out what's going on, it's perfectly straightforward. It can look a bit sort of weird to start with, but you know, well, perhaps I shouldn't say that. Perhaps if I hadn't said that, you would have all gone, oh no, this is obvious. And now I've given you that warning, you're going to be like, is this more complicated than I thought? It's not. Don't worry. So you saw last week, we can use the auto keyword to deduce the type of something from its initializer. right? It really helps us when we've got a long type name. We can just use auto, and the compiler will look at whatever the type is on the right-hand side of the equals and go, okay, I want one of those. It doesn't mean, and I'm sure Ollie stressed this last week, it's not dynamic typing in any sense. The type is fixed exactly at the point of declaration, as always in C++. A variable has one type and one type only, and that is the same for the entire life of the program. So auto is not any kind of dynamic typing. It just means deduce the type from the initializer.
So it'll change because you can have like certain bits and like an input can only hold so many bits and so forth. So if you go over that bit, it won't change the type of the variable or whatever you classify it as.
No, the type of a variable is fixed at the point that you declare that variable, always. Yeah. So here's the thing to bear in mind. Here is the one key to remember what auto is doing. Auto never deduces a const or reference type. Okay? Just remember that, and everything else will be plain sailing. So C++ value semantics by default. If we suddenly had auto-deducing references, that would be really, really weird. Okay, so it doesn't do that. Auto never deduces, plain auto never deduces a const or reference type. This doesn't mean we can't have an auto ref. It just means we have to ask for exactly that. We can initialize a variable, we can write a variable as auto ref, and that means, okay, I want a reference variable and I want you to deduce what kind of reference I have. And likewise, if we want a variable that's const, but of deduced type, we can use const auto.
So can you do const auto as well?
You absolutely can. Do const auto ref if you want, but yeah, that's going a bit far. Did you have a hand up?
No.
Oh. So these are the rules. Auto by itself never deduces a const or reference type. However, we can request it either by putting the ampersand or by putting the const keyword. Come on. So we're going to play this game a few times. I've got an int and a constant, I and ci, and then I've got two references, ref and cref. Now I'm going to create some new variables. They're called A1 through to A4. And I'm initializing them in turn from I, ci, ref, and cref. So, this is a plain undecorated auto. Each of these, A1 to A4, is plain undecorated auto. So, what type is going to be deduced for, let's say, A1?
I guess
Int, absolutely, yes. And A2? And A3? Sorry, did someone say A2 was a const? No, auto never deduces, plain auto never deduces a reference type or a const type. Okay? So A2 is also an int. A3 is also an int. And surprise, surprise, so is A4. In each of these cases, all these new variables, A1 to A4, they're all ints. Right, this is consistent with the value semantics we use by default in C++. This is the right answer. Come on. All right. The same setup, same for variables. Now I've got A5 to A8. And each of these is declared with type const auto. So what is the type of A5, anybody? Const int, absolutely. So the const keyword before A5 says, I want this to be a constant. Deduce for me what kind of constant it's going to be. It's going to be a const int because we are initializing it from an int. And the same thing is going to happen with CI. And the same thing is going to happen with ref because we haven't asked for a deduced reference type. We've asked for a new value. We're going to initialize that value by looking at whatever ref, whatever the underlying type of ref is. But in each of these cases, A5 to A8, they're all going to be const ints. You're pretty good at this game. I'll throw in a little spanner in the works this time. So this is the same as we had before, except instead of const auto, it's now const auto ampersand, a reference to a const of deduced type, a read-only reference to something. Anyone want to take any guesses as to what, let's go with A9, is going to deduce to?
That's const a reference to int, because we have int, so we deduce the int, but we want the reference to I, and we initialize as a const.
Yes, absolutely. So if that didn't come out on the microphone, A9 is going to deduce as a reference to a const int. We're saying we want reference to const something. Please go and deduce the something for me. And it's going to say, well, the type that fits in this case is an int. Yeah.
So if I understand understanding right, A9 will be constant, no way to change, but I, which initialize, can be changed.
So A9 we cannot modify. We can't say A9 equals 12. However, I in this case is mutable, so yes, we could say I equals 12. So A9 is like a new name for I, but we cannot make any changes via that name. So yes, in this case, A9 to A12 are all of type reference to constant. You're doing pretty well. This is the last round now. A13 to 16. All right. What is the type of A13? A reference to int. A13 is a reference to int. Yep. Because I've said, I want a reference to something. Please go and deduce for me what that something is. And the type that fits is int, a reference to int. So A13 is exactly equivalent to if we had said int ref I. Int ampersand I. Int ampersand A13 equals I. I'll get it right eventually. What about A14?
What does
Almost very good. What I said, or what I hope I said, because I was trying to be careful about it, is the plain auto. That is undecorated. That is without any decoration. Plain auto never deduces to a reference type or a const type. We have to ask. So, what A14 is saying, I want a reference to something. Please find the right type that fits. Well, we cannot possibly have int ref there because that would be an error, right? We could not initialize int ampersand from a const int. So this is why we went through so many rounds of this game, was just to get to this little, tricky perhaps, this little surprise at the end, is that A14 is going to deduce its type as a reference to a const int. And likewise 15, that's going to be a reference to a mutable int. And a 16 is going to be initialized as a reference to a const int. This is something that even people who are really well versed in C++ get surprised by. Right? It is entirely consistent and it is the right thing to do. It's just perhaps a little bit non-obvious.
Can you explain how with the auto reference it works in terms of it passing through as a constant? Listen, I didn't quite understand why with the auto ampersand it's different to other auto.
You don't understand, or you do understand?
I don't.
You don't understand why A13 and A14 do something different?
Yes.
Okay. So A13 is saying, I want a reference to something. Please deduce for me what that something is. And the thing on the right, in this case, is an int, a mutable int. So I can form a reference to that mutable int, and that's fine.
Yes.
Okay? I didn't ask for a const reference, so I'm not getting one. With A14, on the other hand, I'm saying, I want some kind of reference. Please go and find the type that works. And in this case, it cannot deduce an int, because if we substituted int in there, so we said int ampersand A14 equals CI, that would be a compile error, because we'd be trying to initialize a read-write reference from something that was immutable. And we can't do that. So the only type that makes sense to go in there is const int. Right?
It was a reference to a const auto for A14, that being effective.
Exactly, yeah. Because then we're explicitly saying, give me a const reference. Yeah. So in this case, saying reference to auto and reference to const auto for A14 will do exactly the same thing. Yeah. So as I say, this actually is consistent and is the right thing to do. It just trips people up sometimes. Even very experienced C++ programmers get slightly surprised by this behavior. So I thought I'd give you a heads up. Perhaps have confused you, but I hope not. The gist of it is, we can never form a mutable reference to something that is immutable, right? And the only way that we can make that restriction work is by having A14 and 16 in this case deduce a const reference type. All right, that's enough talking. Enough talking, let's get your hands on the keyboards. Again, bit of a late start, so we won't have all that long to do this, I'm afraid, because I do want to get the last little bit out of the way so that we can move on to the next module next week. And I don't want to delay you too much this evening. We've got a pub to go to. So, what I would like you to do is to write a function print string, because I love print functions, that accepts a read-only reference to a string and prints that string using cout. Well, I've shown you a few examples of what that might look like. Then in main, just create a local string variable and verify that it works correctly. What I mean by that is verify that your print string function works correctly, right? You'll get that, I hope. Then call your function with a string literal. By string literal, I just mean something in double quotes. And actually, before you do that, perhaps think about whether you think that's going to work or not going to work. So you've now, in your main, you should have two calls to print string, one with a local variable and one with a string literal. I then want you to modify your function, your print string function, so it takes its string argument by value instead of by reference to const. Before you do it, have a little think, try and decide whether you think it's going to still compile or not. Then try it out and decide whether what you thought was going to happen actually happened. And then the final thing I want you to do is, instead of by value, just take it by mutable reference instead of read-only reference. And again, go through the same process. Have a little think, is this going to work? And then try it out. Okay, so I'll give you maybe 15 minutes for that because we are a little bit pushed for time. But have a go, and as usual, if you have any problems, raise your hand and someone will be along to help you out. Okay, so go to guest, guest.law.ac, yeah, that's the one. That's it. This site is not secure. Oh, lovely. I don't know why that's happening. Let's try it out.
Thank you very much for the class.
Oh, no problem. No problem. Thanks for coming. Thank you.
Stavim je dal, then trying to put back.
Okay, this is let's just try and go to like this is very strange.
Why does it happen?
I don't know. It looks fine. All right.
Is it because of browser?
I think it's to do with the certificates on your computer. Let's just try and go to Google. Yeah, okay, that's working now.
So how can I get to this?
Oh, well, I assume you've got like C-Line installed or something like that.
Yeah,
You can do this in one box or whatever if you like.
I'm going to download the last.
Sorry?
To download the last session.
Yeah, did you download it?
Not yet. That's what I'm asking. I forgot what was stored.
Okay. Unfortunately, we found out that if you try and download it here, then it actually interferes with the upload of the yeah.
Maybe they can send.
Yeah. So, but if you go to one. What's up?
Right, who needs
Hello, mate. Yeah, I'm right. Yeah, how you doing? I don't need help, no. All right, thank you.
yes, go on.
Just compiling, take a while.
Yeah, go.
Yeah, 1 hour and a half.
Okay.
Take it. No, just waiting
let's try
to
something.
compile it. I've been holiday already. Yeah, like 12,000 steps ready to go. Some pet projects that are
Okay, so this is just a little Hello World program. So this is an online compiler. You can just type in run, and you can see it prints out Hello World. Okay, so this is enough to hopefully get started with the exercise. You have C line?
Yeah.
Oh, I thought you said you hadn't downloaded it.
Yes, I downloaded. So how can I?
Okay, so if you have C line installed, then you can run C line and you can do this in C line.
Is it possible to save this?
You don't have to save this. Oh yeah. If you have C line,
There you go.
and we can run C line and create a.
There was a free option also from Microsoft.
Yeah, Microsoft
Struggling.
Visual Studio is free as well.
Oh no, you stay away from it.
Look at the hungry.
All right. Yep. So close that. So all we're going to do is we're going to create a new project. What are we going to call it? Well, let's call it
It's not a German cheesecake, I just looking it up.
week 6
Well, there's Bavarian baked cheesecake. There's
exercise.
also German style cheesecake.
Yeah.
You don't use real dough.
Oh no, it's not a dough.
So next week we'll start the next module.
Yes.
Is it available?
Not yet. No, we're going to talk about how we write our own types. So with the
Right, let's just pick something.
I'm really thinking about the object. I've touched a bit with Pascal, but it's not the same.
that will be the module after.
Okay, so the only thing
We have to get the basics out of the way.
we like is that
What days are tomorrow?
With that. Right, so if we press play here, see it'll go away, it'll press our thing, and it's worked. Okay, so you are now in a place to do the exercise.
To be honest, I'm having problem with these STDs. Why do we need to put STD? What is STD?
And so STD is a namespace, which is in fact what we're going to talk about in a few minutes' time. Well, if hang around a few minutes after the money may come from the I really want to get the namespace and stuff.
You said we picked something at the end of this, so I don't think it.
Yeah, but I don't want to distract everyone else. I'm allowed to.
I haven't tried it, but I think somewhere as well. So it's hard to get it. It's a lot. Mary Berry.
C++ for like 2 weeks and I thought, oh, kick back off again. So I've not done any of the functions for ages. So this is just passing by values. And I'm just
That is passed by value, yeah.
values. So
Absolutely.
then I was thinking, oh, I would be passing it by ref because we have to initialize it by reference now. So that would be like, that would be a reference. Then you pass it. Or would that be over
Okay. So what I was doing in the first place was, so I want the function parameter is now a reference to read-only reference to
Oh, because that would be like just a string but used in the library.
yeah, exactly. So that's pretty much exactly what I wanted you to do for print something. Awesome. So that's what I've got.
Yeah.
Yep.
And the string literal, I thought that would just be like double quote.
Yes. Yes.
Why is it unique to a whole lot, or what do you actually So we've done, so those are all done.
Pass in the actual, or pass the actual string.
So you want to build const, you see const.
Sorry.
That's the most important. That's what you've already got. That's basic.
No, I've got. What do you use to copy title? I have just used export.
Yeah, and so we recommend people use, well, if you're happy with Xcode, that's absolutely fine. We have you tend to use C-Line in this class just because it works on like Mac and Windows and Linux, so everyone's on the same page, it's easy to help. But yeah, if you're comfortable with Xcode, that's
No, the only reason because remember I used to be like Windows until I started doing dev work, and then I was thinking, oh, so the Mac's not as easy to do as compiler, so we can go for
Yeah, no, that's absolutely fine. If you want to download C-Line, you get a month free. We can sort you out. Paid product, we can sort you out.
Oh, yeah, I remember it. Okay, cool. So you can pass by
Well, I don't know what the hell that is.
literal and by value.
I'm doing good. I have Git in share, so I can commit and push it up. So I remember you told us about it. I got called in like making the whole class. It doesn't compile this part when I choose a reference. And could you explain once again why I cannot do the auto deduction for
Okay, well, try
or std string?
std string and tell me if it works then.
Yeah, and it does just doesn't work. We just want to.
So the reason is for basically reasons of CPU function and efficiency, I guess. The type of a string literal is not standard string, right? It's an array of characters, right? Which is, and so when you use auto to deduce the type, you're going to get an array of characters, but because of our awkward C history, it's actually going to deduce itself as a pointer to an array. Right? Now, that's fine because standard string knows how to. We know how to construct standard string from an array of characters. That's
It
fine.
didn't fail in the other two when I passed it as a value.
Yeah. So if we just go back up to your function definitions. So, what happens when we call, let's wait for a second, print string that. Standard string STL. What happens is we pass an array of characters.
And there's the conversion
And
going on.
and what it does is it creates a temporary standard string.
I've got shit off of this one.
Standard string that produced really as long as
next time
your
I make it up.
and that's fine, because we use
It's alright, I know the would be nice one. Thanks. Oh, I'll hold it on if you've got it. No, thank you.
the top one.
Okay, but I'll probably like.
Oh, imagine that was Const string.
Alright. Yeah.
I know it's
So
annoying.
you do you have a charger?
Now, this is kind of where a bit of magic happens, because what it does is it creates a temporary standard string, and then it uses that string to initialize the construction. Right? Now that's a bit of magic. And then that string only lives as long as you're in the function, then it gets thrown away, and that's fun.
It's the same things that happening before when I had like const, it creates implicitly the variable. And when I take away const, it doesn't create and it doesn't compile.
Yes. So, in the third case, print string ref.
Yeah.
In theory, we can have the same thing happen. See it? In theory, we can have the same thing happen. We can create a temporary standard string and use that to initialize it. But a very long time ago, C++ decided, or the creator of C++ decided to protect you from doing silly things, right? Because if you have a mutable reference, the expectation is you're going to affect the original variable. Right? But actually, what would happen in that case would be you'd only be modifying some temporary value that can be thrown away. So, if you are attempting to use temporary with a mutable reference, to usually assign, you probably made a mistake. So C++ protects you from that, at least that's the motivation for it, to protect you from these potential errors. So it doesn't allow a non-const reference to terminology to bind to a temporary value. So this is the really important difference, really crucial difference between const references and mutable references. So I kind of want to bring out this exercise. Is that you can use temporaries with const references.
You don't need to
That
use this
temporary
at all.
will live precisely as long as the reference scope. You can apply temporaries.
Access a binary with unstable API or something, or if it needs to be like switched out. Use unstable APIs, then you should not be. You just let Windows take care of it. Yeah, this is a much bigger thing. I can help you.
Yeah.
Declaring function comes before or after the name.
You don't need the word function in there at all.
Anyone else needs to
So say we have the return type, the name of the function,
Who's done it?
and then its argument types. So
Oh, I've got it.
that should be okay.
No, it's not.
Variable full print string tag void. That's weird. Oh,
Yeah, Tom.
yeah, you've just got these things in slightly the wrong order.
Birthday.
Yeah, you missed that at the beginning. Oh,
Well,
no,
no,
cake
because
as
you
I
can
can.
actually type
Yeah.
it.
But have a cake as I can.
And again, you've done the same thing.
This timing. Are we gonna sing happy birthday?
Oh, that works.
Not quite, because
Yeah, well, you're not calling, you have to still call your parent string.
Someone can join by.
yes, it's here. Where is it?
That's a good point.
So you have to, from main, you have to make a call to your
There's a
print
common
string.
room there. Maybe there's some plastic
Like
knives.
for,
Common room.
Yeah.
No.
Come on, are you busy?
yes, that one has a print string.
Where am I going?
String. Let's call this variable something else. Let's just call it. Otherwise it gets a bit confusing when you've got a function called main and a variable called main. So you want to do that. Semicolon at the end. I told you I always do that. And there it goes.
Yeah, where is it? Yeah, it does. Thanks.
Okay, who managed to do at least some of that successfully? A couple of hands. Who managed? Well, did you both manage to do all of it successfully? So 2 of you put your hand up for you didn't do. Anyway, I was expecting the second group to be a subset of the first, but anyway. What I think I might do is actually, I do have a sort of tricky homework revision-y thing for you at the end, but I might leave this to the early part of next week, since a lot of people seem to still be in progress on it. And we have 20 minutes, and I do just want to cover this last bit, which is the very last thing on the schedule for this module, so then we can finish on time without dragging over and having next week as a kind of mixed session. Okay, so as usual, the slides will be available. This video is hopefully working today, so yeah, if you want to take a photo, be quick.
Try. Yeah.
All right, let's talk about namespaces. Who hates all that std : stuff I make you type all the time? Yeah. You're about to find out why I keep making you type it. So, when we're writing programs, well, you know, this is a beginning course, so you've just been doing little kind of example programs so far. But in general, we're writing programs to, you know, solve real-world problems. We don't want to reinvent the wheel all the time, right? Don't want to have to write everything from scratch. We want to make use of software that other people have already written for us. We want to build on top of what are called software libraries. These are like, as I say, bits of code that other people have written that we can use so that we don't have to, you know, start off by asking the operator, you know, really low-level code. Every practical piece of software uses libraries. And in fact, we may use libraries from many, many different sources. If you're writing some really, really big program, you might have hundreds of different libraries. So this might raise a problem, because the author of library A has no idea that I might combine their work with library B over here, in general. So what happens if the authors of these two libraries, who have never met and don't know each other and have no way of knowing what the other one is doing, what happens if they decide they choose the same name for their functions or for their types? This can lead to name clashing. This can lead to problems. So I'm going to show you a very silly, contrived example. This is, because it fits on a slide, you can take this as indicative of a real-world problem. This specifically, this is a bit simplified from what happens in real life, but it shows you the idea. Imagine we're writing a game, you know, Western, so set in the Wild West. You know, this is Red Dead Redemption 3 that we're writing now. And we're using a graphics library that draws things on screen. So we've got our cowboy, he's a character, and we've got this function draw, which says we want to draw our cowboy sprite, polygon, whatever it is, on the screen. So that's in the graphics library we're using. We also got this gameplay library that handles like all the user actions. You know, handles the input, what happens when you press the X button or whatever. And this has got a function called draw, which unholsters the pistol. Okay, so then we're processing our game. We're making use of the graphics library and the gameplay library, and then we've got our function that processes all the character actions, and we call draw. And what happens?
Either one would get called depending on the type.
The second one got called because the include of gameplay went later, so the draw from the second one will be in memory.
So you think the second version of draw is going to be called?
Yeah, because the gameplay was imported later.
Because gameplay was included later. Michael's got his hand up.
Yeah, it's not going to compile because if it cannot resolve a name conflict.
Actually, as written, with the two draw commands as forward declarations, this will compile. What it won't do, most probably, is link correctly. So your program won't build, but it's going to be for a slightly different reason. And actually, this isn't quite as bad as it gets because there are times in which, if I had written this very slightly differently, in which your program will build, will compile and link correctly, and you have absolutely no way of knowing which version of the function is going to be called. Right? When we get to inline functions,
Yes.
and weak symbols, and the reasons for it are kind of a bit beyond what I want to go into today, but the point is this. If we have two functions with the same name, same argument types, that do two different things, that is a problem. But in both of these cases, draw is a reasonable name for this function, right? If we want to draw something, as in physically write the pixels out on the screen, in computer graphics we call that drawing. Draw the cowboy, that's reasonable. From the perspective of the people writing the gameplay code, well, you know, we're having a duel, we want to draw, that's fine. It's a decent name for the function. And yes, this is silly and contrived, right? But this actually can happen frequently. This has been a known problem for, I don't know, 50 years. And there is a solution that people have been using for 50 plus years. And that is prefixes. So one thing we might do is to add a few extra characters onto the front of our function names, type names, that mark this function as belonging to the graphics library or belonging to the gameplay library. Right? To use a usually abbreviated name of the library as a prefix to every single function name. So, you know, a silly example from the last slide, we might call the function gfxDraw, graphics draw, right? To differentiate it from, perhaps the other one might be like I don't know, gameplay draw, TV draw or something. And this is in fact very common, right? This is a solution that C has used for 50 plus years. Other related languages also use this same solution. So I don't know if anybody's ever done any Objective-C on Macs or iPhones, but Objective-C, you prefix everything usually with a 2-letter, 3-letter sort of name of your library. So all the standard Mac functions were NS something for this reason. Some older C++ libraries also use this approach. A notable example is Qt, which prefixes all of their function names, all of their types with the letter Q. Because you hope, in that case, no other libraries that you're mixing this with have that same prefix, and so the names are independent and will not clash. And that works, and that's fine. It just gets a bit long-winded, a bit verbose. And so C++ has effectively a built-in way of handling these prefixes. Rather than making you manually add it to the front of every single function name, every single type name that you write and that you call, C++ has a built-in solution, which is namespaces. So namespaces are a way of grouping a set of related declarations, functions, types, aliases, templates, what you name it, entities, as they call it officially. We can group these together, say these things belong together. These things should have the same prefix. These things belong to the same library. And we can give that prefix a name, and that is a namespace. And this means that we can reuse the same short names for functions, say. We could have a draw function in namespace A and a draw function in namespace B, and these things would not clash. It's as if we were using these same prefixes that we had in C, but without having to write them, in some cases, without having to write them absolutely everywhere. So when we call a function from a particular namespace, we write the namespace name followed by a double colon followed by the function name. So we've already seen this. We've seen this several times. We've seen it several times today even. Everything in the standard library belongs to this namespace called std. And so whenever we use a function or a type from the standard library, we prefix that name with std : : because we might be using another library that has a class in it called vector, a type called vector. Because vector is pretty common, it's got a mathematical meaning as well. Perhaps we're using a linear algebra library to do all our complex 3D geometry. They might have a vector type. And we want to make sure that the vector type from that library doesn't clash with the vector type that's in the standard library. So everything in the standard library has its std : prefix. That is, it's in the std namespace. And we can declare our own namespaces as well. So we're going to fix our little example from a couple of minutes ago. We're still going to have our draw function, but this time we're going to put it in a namespace called gfx. As I say, namespace names are typically short, but hopefully reasonably unique. We don't want to have clashing namespaces, then we're back to the same problem we had before. But now we've got a function called draw in our namespace gfx. And now we've got a second namespace called game, and within that, again, we've got a function called draw. But these are now two different functions. They live in different namespaces. So in another part of our code, we want to make use of these functions. We say gfx draw. That is, use the draw function that belongs to the gfx namespace. And that displays it on the screen. And we can also explicitly call the draw function that belongs to the game namespace. That is, game : draw. Use the draw that belongs to game. That's explicit and unambiguous about which version of the draw function I want. You're desperate to ask a question, Saad.
Yes. So namespaces, can they only be declared in a header file, or can they be done in
They can be in implementation files as well, and usually would be.
Okay. Great.
Yeah. So I'm going to talk more about header files next week, but yes, you would usually use the same namespace in the header and implementation. Yeah.
Yeah, but if you have objects like classes and structs, how would that be then? The class name : gfx then function.
If you were writing an external definition.
So you had a class, let's say, and it had its own namespace, a function in its own namespace for whatever reasons. How would you then?
You cannot have a namespace. You cannot declare a namespace inside a class. As it happens, classes act rather like namespaces, but that's something we'll talk about a while in the future. Yeah.
So namespace will collect our own functions?
Yes, effectively, yeah. A namespace says this chunk of functionality belongs together, right? So, as we just seen, to declare things as belonging to a namespace, we use the namespace keyword, followed by the name, followed by a bunch of declarations in curly braces, just as we saw on the previous slide. But here's the magic thing. Other code that it lives within the same namespace doesn't have to use the prefix. All our code that lives within a namespace does not have to use the prefix to refer to other names within that same namespace. This is what makes namespaces better than this C way of doing things, of using a fixed prefix as part of our type name. It means that, yes, our code that is inside our functions tends to be much less verbose compared with C-style prefixes. We can also have, and up until right now, you have entirely written code which lives outside of any namespace. And such code is said to belong to the global namespace. Right? Code that doesn't live within any namespace declaration is said to belong to the global namespace. Yeah.
What STD?
STD.
Yeah.
Yeah.
So that was one.
So STD is a namespace, yes.
Yeah. Okay.
It is the standard, the namespace that belongs to the standard library.
It's a special one.
Yeah.
Don't stick your stuff in it.
So here we're declaring a namespace maths, and inside it I've got a function called sum. And what this does is it iterates over a vector and it adds together a vector of floats. It just adds together all the things that were in that vector. Note, by the way, I'm taking the vector by Const reference. I don't want to copy it, but I don't need to modify it. And we can use auto in the for loop, range for loop, if you haven't seen that before as well. Now I've got another function called average. Well, how do we calculate the average? We take the sum and we divide by the number of things, right? So all we need to do is to get the total and return the total divided by the number of elements in the vector. But here's the key, is that these two functions, sum and average, are both in the same namespace. So within our average function, we don't have to type maths : sum. I mean, we could if we wanted to. It wouldn't be wrong, but it's not necessary. We can still use this nice short name here. Because it's going to find it in the same namespace that we're already in. So then we close the maths namespace. And then we have our nice main function. Main is always in the global namespace, by the way. If you are allowed to have a function called main within a namespace, but it doesn't have any magic. It's just an ordinary function. And let's just create a vector and calculate the average, the mean. We want to call the average function, but main is not inside the maths namespace, so we have to explicitly say, I want maths : average. All right. We're out of time, so I'm going to skip namespace aliases. It's just a way that you can, if you have a very, very long.
Can we get back just from it?
Oh, yeah. Too far. No, you wanted the next one, right?
Well,
This was the example that was just on the screen. As I say, all these slides will be available. You can download the PDF later. But you can, if you have a namespace with a very long name, you can give it a nice short name as an alias. This is just the very last thing I wanted to say is about using namespace. C++ has this facility that you will sometimes see in beginner tutorials of using namespace something or other. In particular, you might often see using namespace std. And what this does is to say, okay, for the rest of this scope, just make all the names that are in this namespace available without me having to type the prefix. And you might think, that's brilliant. I hate having to type std : vector. I hate having to type std string. Why can't I just type vector and string? Well, yes, it seems attractive at first sight. Unfortunately, this undoes the entire point of using namespaces in the first place. Because the standard namespace in particular is absolutely huge. There are hundreds, if not thousands, of names of things in there. Very, very common names. Names that are extremely likely to clash with names that you have chosen for your own functions. So if you use this using namespace technique, it puts you at great risk of clashing, of making mistakes, of either having ambiguous function calls or, even worse, having unexpected functions get called because some function overload happened to be a better match than what you hoped for. And yes, it's particularly the case for large namespaces like std. So my recommendation really, and I'm sorry to do this because I know everyone hates this std and goes, why do I have to do this? My recommendation really is avoid the temptation of using namespace unless you really, really know what you're doing. Right? And if you find most experienced C++ programmers, they will not really use this ever. Right? And in particular, and this is very, very important, never, ever, ever put using namespace in a header file. Right? That is always wrong. So for those who know Python, this is kind of like, I always forget, you can do like input from module import star.
You never do that.
But you never do it.
It's not allowed. Like, it is technically possible, but it's very bad practice.
Exactly.
Because then you break to your namespace all the variables that you're probably gonna overshadow at some point.
And that is exactly why this is a bad idea. So may not have come out on the microphone, but in Python you can do like from module import star, right? And that just imports every single name from that module but it imports it into your current namespace and is seen as, while it's technically legal in the Python language, it is extremely bad practice and will get you shouted at by your fellow programmers in code review. And using namespace is the C++ equivalent of doing that. Bad practice, don't do it. And ladies and gentlemen, that's it.
What's the relationship between modules and namespaces?
None whatsoever. No. But this is not C++ modules. This is C++ London Uni modules.
Yeah.
That's why I gave it a capital M. Because it did have a lowercase m, but I thought that's not going to be valid very soon. Anyway, congratulations. You've all made it to the end of Initial C++. I've kept you here for 6 minutes longer than you had to be. But there we are. We've got to the end.
Yay!
Next week we'll be starting our new module, and next module, custom types. And we've also got fun end of module questionnaire time, which everybody loves.
So prepare.
So yes, just a few lightweight questions on the C++ you have learnt over the past few weeks. Mostly so you can know how you got on, and also so we can know how I got on. I suspect you'll all be really good on Const and auto and references because that was Ollie's week. But anyway, that's next week's problem. I do have, this is going to be tiny, so if you want to come to the front and take a photo, you're more than welcome. I do have a really in-depth homework exercise. It will take quite a while. It's not easy, but you can do this with what you have learnt on the course so far. So it's too small to read, I know, but by all means come to the front and take a photo of it. Otherwise, as always, the PDFs are available.
When is this going to be posted?
Hopefully in about 10 minutes. And that's it. That's it for Module 1. But also, very special announcement that it is almost just about, I think we're a couple of weeks over, but it is the second birthday of C++ London Uni.
Yay!
Hooray to us. And Kat has very kindly made us an awesome looking cake. I'm sorry to anybody watching online who cannot appreciate the majesty of this cake.
You miss.
But yes, thank you very, very much.
Yeah.
Especially to Kat. Yes.
So yeah, round of applause.
Yay!
And for everybody online, we will bid you goodbye and we will tuck into our cake and see you next week.
But the problem is